Let's see the one more problem in the concept of simple stresses and strains. Figure shows a rigid bar ABC hinged at A and suspended at 2 points B and C by 2 bars BD and CE made of aluminium and steel respectively. The bar carries a load of 2000 kgs midway between the B and C. The cross-sectional area of the aluminium bar BD is 3 mm square and that of the steel bar is 2 mm square. Determine the load taken by the two bars BD and CE. Modulus of elasticity for aluminium E suffix AL 7000 kg per mm square. Modulus of elasticity for steel, that is E suffix S 20,000 kg per mm square. So here it is given the hinged bar ABC. So it is the rigid bar hinged at the point A, and the ABC bar is suspended by the two rods. One is the aluminium rod BD, another one is the steel rod CE, and applying the load on the ABC hinged bar. So 2000 kgs, that is the midpoint between the B and C. So here it is given the data, load is given, load applied on the bar is 2000 kg, and also given the cross sectional area of the aluminium bar. Let consider A suffix AL 3 mm square, and also given the cross sectional area of the steel bar. Let consider A suffix S 2 mm square, and also given the Young's modulus for the aluminium and also steel is given. Now we have to determine the load taken by the BD bar and CE bar. Here ABC is a rigid bar, it will not be bent and also it will be remains straight only, but the aluminium and steel rod will extend due to their elasticity. So in the figure shows the position of the rigid bar after the aluminium and steel rod have undergone their extension. So in the second diagram it is represents the position of the rigid bar. So from AC is the initial position and it will goes to the AC1. It is the final position of the rigid bar after the steel and aluminium rods undergo their extension. Let consider initial position of the aluminium rod is the BD, and applying the load due to their elasticity it will go to the deformation, that is the position is B to B1, and similarly initial position of the steel rod is CE. After application of the load it will goes to the deformation, then it will goes to the position C1 to E. Here delta AL is the deformation of the aluminium rod, that is the B to B1. Delta ST is the deformation of the steel rod from the C to C1. Let the tensions in the aluminium and steel rod are the, let consider R kgs and the S kgs respectively. So here we are applying the load 2000 kgs on the rigid bar, but due to this one, so tension it will be created in the aluminium rod. So obviously, so the tensions it will be generated, that is the opposite to the applied load direction. Let consider R kgs for the aluminium rod and S kgs for the steel rod. So since the rigid bar remains the straight, the extension of the CE and BD are proportional to their distance from A. So we can be solve another way also. So here observe, there are the similar triangles are there. that is the triangle ABB1 and ACC1. These two are the similar triangles. So from the similar triangles we can be say that AB divided by BB1 equal to AC divided by CC1. And we know AB distance is the 1 meter. So AB equal to 1. And BB1 is the deformation of the aluminium bar, that is considered the delta AL. Similarly AC is given the distance is 2 meters divided by CC1 is the delta steel. Let us consider delta S, deformation in the steel rod. So AB equal to the 1, BB dash equal to delta AL, AC equal to the 2 and CC1 equal to the delta S. So from the similar triangles we can be written as 1 by delta AL equal to the 2 divided by delta S. So delta S equal to the 2 into delta AL. We know that one formula, delta equal to PL by AE. So delta S first we have to see. P is the applied force on the steel rod, let us consider the PS. LS, length of the steel rod, let us consider LS, divided by AS. AS is the cross sectional area of the steel rod. ES is the Young's modulus of the steel rod. So equal to the 2 into delta AL. Delta AL equal to nothing but PL by AE, delta equal to, similarly delta AL equal to the PAL. So load applied on the aluminium rod into length of the aluminium rod AL divided by cross sectional area of the aluminium AL into the Young's modulus of the aluminium EAL. So here observe the length of the steel rod and aluminium rod initially is the same. So this equation we can be written as here PS load or maybe tension in the steel rod is the, we are considering the S. So have to replace PS with the S. LS, length of the steel rod, initially let us consider L, divided by cross sectional area of the steel is given 2 mm square, and the ES it is given the, so 20,000 equal to the 2 into PAL. So it is the tension generated in the aluminium rod. Let consider here R. So length of the aluminium rod, let consider initial length is the L only, divided by AAL, cross sectional area of the aluminium rod is given the 3, EAL it is given the 7,000. So then here LL will be cancelled, and also we can be cancel. So this 3 digits of the zeros. So this side also 3 digits of the zeros. Then equation will become the S by R equal to the 80 by 21. So now consider the equilibrium of the rigid bar, taking the moments of the forces on the rigid bar about the end point A. So we have momentum at the hinge point A, we can be say that one the, for equilibrium condition total momentum equal to the 0. So this can be, we can be written as, so one moment will come to the, due to the force 2000 kgs, another two movements are the R and S, tension in the aluminium rod as well as tension in the steel rod. So 2000 kgs in the downward and R and S tensile forces in the upward. So upward direction movements, so R into the 1, so this is momentum R into the 1 plus S into the 2 equal to the 2000 into 1.5. So this equation also it can be written as R plus 2S equal to the 3000. So we know the relationship between the S and R. S we can be written as S equal to R into 80 by 21. We have to substitute in this equation R plus 2S equal to 3000 equation. We can be written as R plus 2R into 80 by 21 equal to the 3000. So this can be, LCM is the 21. So then the 21 into R plus 160 R equal to the 3000 into 21. So from this here we can be determine the R value is the nearly 348 kgs and nature of this load is the tensile load. So we know the relationship between the S and R. So S equal to the R into 80 by 21. Substitute one here. S equal to 80 by 21 into the R value is the 348. Then S is the 1326 kg. Nature of the load is the tensile load. So this is the solution and thank you.